This is problem 132 from chapter 12. Starting from rest, a bicyclist travels around a horizontal circular path. The radius of curvature is 10 meters, and if this is a circular path, that would be the radius. At a speed of 0.09 t squared plus 0.1 t meters per second, where t is in seconds, determine the magnitudes of the velocity and acceleration when he has traveled 3 meters. So we want the magnitude of the velocity and the acceleration from our equation sheet. Equation 1215 tells us that the velocity vector is equal to v, and that's pointing in the tangential direction. We have an equation for v here, but we need to know what the time is at 3 meters in order to find the velocity when the cyclist is at 3 meters. And we have acceleration here. The tangential component is v dot. Well, we can easily find v dot by taking the time derivative of v. And then we have v squared divided by rho. We were given rho, the radius of curvature. If we find v for the velocity vector, then we can just square that for our acceleration. So I have velocity as a function of time, but I need to know what time is when s is equal to 3 meters. So I'm going to use equation 12.1, which relates velocity and position and time. And I'm going to bring the dt over to the other side of the equation and say ds is equal to v dt. And then I'm going to integrate. And let's see. I think we have to assume that at t, when t is equal to 0, s is equal to 0. It doesn't specifically tell us that in the problem. So then we can integrate going from 0 to s, and on the other side from 0 to t. So when t is equal to 0, we're saying s is equal to 0. Then we're going to take our equation for the velocity, stick it in there. So we're going from 0 to s, from 0 to t, 0.09 t squared plus 0.1 t. Then we integrate with respect to t. And on the left-hand side of the equation, when we integrate, we just get s minus 0. And on the right-hand side of the equation, we have 0.09 divided by 3, which gives us 0.03, and this is t cubed, plus we raise the power to 2 and divide by 2, and we get 0.05, and this is t squared, and we're going from 0 to t, so this is what we would get. So this is the position as a function of time, and I want to know what time is when s is equal to 3 meters. So now I'm going to say s is equal to 3, and we need to solve for time. Now, you can use a computer to figure out what time is. Or maybe your calculator. You should get the only real solution for this equation is t is equal to 4.1473s. So you know that time is not supposed to be negative and time is not supposed to be imaginary. So we have now the time when s is 3 meters. So then we can take that and put it into our equation for the velocity. You can do that on your own. We should get the velocity when t is equal to 4.1473 just by plugging that into our equation for the velocity. 1.963 meters per second. This is the magnitude of the velocity, which we can see from that equation. And we need the magnitude of the acceleration. Acceleration is equal to v dot in the tangential direction plus v squared over rho in the normal direction. So we're going to take a time derivative of our equation here to get v dot. So that is 0.18 t plus 0.1. And then we need v dot when t is equal to 4.1473. And again, you can plug that in on your own, and you should get 0.8465 meters per second squared. And now, well, we don't really have to write the acceleration vector, but we'll do it anyways. 8, 4, 6, 5. And then we have v squared at 3 meters. V is equal to 1.963. So we square this and we divide it by rho, which is 10 meters. This is in the normal direction, and the units here should be meters per second squared. We want to find the magnitude of the acceleration. So we square both components, add them together, take the square root. This is supposed to be equal to 0.385, and we get 0.930 meters per second squared. And that concludes problem 132.